So of course, there's probably very little in this life that I can do conventionally. So I'm going to take a moment and provide a little bit of background and an intro for Dan and Patrick, because in some sense, as undergraduates, they've been thrown into the lion's den. Do you mind actually just flipping to that timeline slide? So the work that they are in, or they engaged in this last semester, really dates back to actually about 2004, so almost 2 decades ago, a set of ideas while I was at the University of Toronto, where we started conjecturing that statistical inference mechanisms could detect and find emergent patterns that arose in a system at a very low level that would permit or suggest the construction of a hybrid type of computer system that married biologically motivated statistical inference mechanisms, which have a promise of scalability and low power implementation to add to a computer system the kind of things that we can't get from it, which is the ability to find inherent shortcuts and patterns in how it's behaving and exploit them automatically. So the hope was that if we could convert the problem of building a computer into one where you preserve the deterministic model as the programming model, but you offload its performance into figuring out how to make statistical inference scale and be power efficient. Okay, so these are pretty heady, lofty ideas. But since that period of time, we've had some very interesting, fun milestones, including apparently the fact that somebody saw fit to give me tenure, which, despite me, and I got a career NSF career award around some of these ideas. So a lot of the work that they're going to talk about today is us finally having an opportunity to have the machine learning technologies catch up to what we were hoping for, so we could try some of our conjectures out. Okay, so but along that way, we built systems that tried to exploit some of these ideas to automatically scale computation without ever looking at the code. Okay, that was some work published at ASPOS in 2014. In 2016, we actually built a neural net accelerator, attached it to a computer, and saw that our model actually gave rise to a real interface where a computer's execution at a very low level could automatically be hooked up to a neural net and actually produce feedback that allowed some of these shortcuts. Now, aggressive out there research, I believe, happens because we are a community of supportive people encouraging risk and going out there and saying crazy, stupid things. So these poor undergraduates are now under the risk of dealing with my crazy. So with that in mind, before even they get to an end, they deserve some applause for surviving this. All yours, guys.
Thank you, Professor Ababu, for that introduction. So we have this background of the ideas behind our work, and so now we'll get into what exactly we did, because these are pretty heady ideas. There's a lot of thought behind them, but it's important to be able to concretize and actually test out some of the theories and hypotheses that we have, and that gets into what we did this semester. So our hypothesis, it says on the screen, we use low-level binary representation in the form of what we call state vectors through a program's execution. We believe that it can be exploited to improve the performance of that computer using neural networks. So as in previous works, but in a more general sense, we will take all of the memory of a computer, all the line them up as a state vector, and then try and detect patterns and changes, so that if we see a recurring pattern or some other kind of thing that, say, a neural network or other machine learning techniques can exploit, we can use those to improve execution and to learn more about the underlying processes and the machine itself. Specifically this semester, we worked with the microchess program running on the 6502 microprocessor, and we hope to bypass deterministic computation by offloading execution to neural networks. So bearing the idea of this state vector computer is deterministic. It goes through specific instructions that carry it to different points in a vector space, and taking that and using statistical inference and neural networks to create a model predicting not necessarily exactly where it will go, but an idea of what it will.
And why is it a good application to start with?
It's a good application because we'll get into it in a second, but actually on the next slide. But starting with the 6502 and microchess, the 6502 is a processor from the 1970s that was used in the Apple II and the Kim 1 and several other home computers. So it's a very small computer compared to today's modern standards. It only has 64 kilobytes total of memory. It's a good processor. So in that sense, it's pretty easy to, or a lot, I shouldn't say pretty easy. It's a lot easier to deal with that than any megabytes of RAM or total memory. And you're able to view the whole machine, the whole deterministic process, but it's still large enough where it's a general process. This computer can execute a lot of different things. So we picked the microchess program. It's the first program that was built for the 6502 as a kind of game. It was built by someone named Peter Jennings, who then sold it through mail order distribution. It has kind of a fun history. I'd recommend looking it up after. But we did this using a simulator.
It's from Canada, by the way.
That's true. So we have a custom 6502 simulator that goes through, and it's a C program that runs on an x86 architecture, but you can go through and execute each individual instruction of the process, and it's able to create traces and create those state vectors that we were talking about, where we're able to take a snapshot, collect all of the memory, all of the registers, put them together and get that state vector. So again, the Y, it's much smaller than a modern computer, but it's still a general purpose computer. So in the image here, you can see a few images of what it actually looks like to play micro chess, which we'll do in a little bit. But this is an example of what a trace would look like, where each black and white pixel is either a 0 or a 1 for a bit. And you can see how it changes over time. It's a stochastic process. And the goal would be to go from somewhere up here to somewhere down here to skip execution using our statistical techniques. How is this research related to the previous works? In the past, with Ask and with Dana, it used something called online learning, where a neural network trains as a process is executing, and it uses one example each time to improve and to go through like gradient descent and reset the weights. But this time we're using batch processing. We already have the program executed. We already have all of the traces. And as a result, we can do more. It gives us more freedom and flexibility in terms of the networks that we can try. We can try different architectures of our neural network. We can try different parameters. We can see what works and what doesn't. And instead of going along with the program as it's running or with the system as it's running, we can take a step back and we can see what works, what patterns are we observing, and have more of a data-driven approach as well, where we collect everything that's associated with our process and make sure that we're doing the right thing and what we're saying we're doing, and that that's matching up, and also that we can test more options. However, we're going to do some quick math. And so we have a custom piece of software in the 6502 and as a simulator. And we also have quite a lot of data that we're going to be dealing with, because for each state of the 6502, it's 64 kilobytes of memory plus 8 bytes. On average, it executes about 14 million instructions per board state. And in just our experiment that we ran this semester, it was 358 board states, but we have many tournaments that we're hoping to go through. So when we produce a trace of this data, it leads to quite a lot. That's a lot of data. And so the question becomes, how are we able to use this software, but also how are we able to deal with this massive amount of data? And that's where the MOC and NERD come in.
So we have this problem, we have a lot of data, we have a lot of custom firmware, and we have a lot of things to do with it. So how do we bring this problem into the physical? This is our basic framework that we set up. We have our two main computers, the JA CPU and the JA GPU. And as you can see, we have a lot of storage with them as well. So that's where we keep our large amounts of data. Along with it, we have our VMs, where we're able to run our custom software that we have to be able to run the 6502 and all of our experiments, and being able to hop into them from anywhere, obviously with SSH, and being able to work not only with our group that we did our research on this semester, but with Sanjay as well. He's able to work on the Jupyter environment, which we're able to pop up on these computers and be able to work together there. As well as being able to see statistics of our computers outside of the computer, making sure we have the space and seeing all of what's going on in the inner workings there. But the actual process of collecting our data, we start with the PGN notation. These are tournament games of chess notation that you can get offline, online. And there we have many, many games of many tournaments. And using these games, we're able to extract multiple games from these tournaments and put them into a state that's easier to work with. First, we start moving it to a Fenn notation, which is Forsyth-Edward notation, a common notation. And using these boards, we're able to put them into a state where we're able to use the microchess state notation and run them through our 6902 to be able to get both a start state of a board and an end state of a board throughout a play. After we've collected these boards, we're able to
Maybe just to clarify, so the board state we get from online, that's what we call the start state. And then we're gonna let the entire computer, including the program, make a move. So we're letting the program evaluate and go 14 million sets of instructions on average, it executes, for it to produce its response to that board state. So that's so this is not neural networks at all right now. This is just sort of gathering some evidence of these kind of movies about what this program really did. Okay, so that's what they mean when they say start end state. It's the start state was given, the end state was produced by this computer, right?
And it's a lot of data because you're getting literally every full fidelity step trace, every bit that
Yeah, so we have, while we run, we gather every state of the machine as it goes through. However, the particular study that we're gonna focus on uses a subset of it, but that's just because it's a starting point.
Yeah, so when it comes, we took one tournament, we took 358 start end state pairs. So the start state is some situation present in a game. This was a tournament from Hamburg in 1868. So back several decades ago, someone was in this position and was faced with what move should I do? And then we don't evaluate what that person did or what the ideal chess move would be. We evaluate what exactly would the micro chess CPU program as created by Peter Jennings, how would it evaluate that and what move would that program make?
It's
So
pretty
that's the end.
competitive as a player, Michael? No, right? No?
But I mean, on an 8-bit computer,
Yeah.
back in 1970 something, it's incredibly competitive. Compared to Deep Blue, not a chance.
Yeah, compared to the average human,
I don't know, I can't even play chess, so what do I know?
I would say it's surprisingly good, but there's also a number of issues outside of that as far as the micro chess program itself. When we demonstrate it later, we can show that like you can move any piece anywhere on the board. It doesn't really have like, oh, you can't do this move. This is not a rule. Like you can do anything you want. So that's kind of a danger, which is why we chose pre-set up boards and let the computer play through it so that we know that.
So like, what's like the intuition behind the logic on that programming effectively? Like,
what it does is it goes through and it evaluates each potential. It's either like a bunch of candidate moves and it evaluates it in a chess process where you check for checks and like, see, should I move out of a check? Then you check for captures, like what pieces should I take? And then you look at strategic position. And so it goes through these, and then based on, I'm not sure the exact like how it evaluates, but it just is it some kind of point rating. And then based on that, it picks the move with the highest point rating and selects that. So it does have some kind of strategic intuition.
is that possibility also like selects some distribution over that or anything?
Yeah, because it's programmed to play certain openings and certain moves. So for example, if we're hoping that like when we study beginning moves that it will be able to see that like it always happens to play these 3 openings and you can start to detect, like, we can build a model for where it is without actually even looking at any of the source code or the program. So when we run these experiments, we have this start state, we have this end state. We get it into a form where we can input it into a neural network because 65,000 bits is a lot of input neurons. So we convert it to only the bits that can possibly change. We use that as the input layer, and we use the same for the end state as the output layer of the neural network. We use tools that we built, we call it PyTool, where we can input a series of parameters that we want to sweep, and we do a grid search where we go over different numbers of epochs, different learning rates, different functions for like a threshold value and other things like that. And we produce a bunch of neural networks with these configurations. Then we go to our test set and we test it on these neural networks. We see how it performs, where it makes the errors, and hopefully in the future, we'll be able to start interpreting why. Here are some of the results from our experiments. These are what our files look like. It produces a lot of files and a lot of data, and it's all reproducible. We spent a lot of time building tools to make sure that we can reproduce this data. We've done a lot of testing to make sure that like this is stuff that even though it's quite a lot, we can, like if we hand this to someone else, they'll be able to reproduce like what we did this semester. So back to our platform, what are the actual tools that we use? Like we have this nice idea of, well, we're gonna take these board states from microchess and we're gonna put them into a neural network somehow, and then we're gonna train the neural network and then we test it. But how do we actually do that? We built a lot of software underneath it using our virtual machines, using the data stores that we have. So the first step in our process is how to even SSH into these virtual machines. And so we just type SSH, but there's a bunch of things in our repository called NERC tools that we use in order to be able to use OpenStack and get into these virtual computers. This is an example of one of the scripts that we use, but they help in the sense that these are virtual machines. And so similarly to if you just set up an instance of AWS or something like that, if you leave the virtual machine running, it will keep running. And so you need to have a way to call the machine where if you're inactive for a certain amount of time, or if you used it for like however many hours, you want to be able to cut it off to save your research budget. And so we have tools that if for some reason we leave our computer and forget to exit out of the shell, or if it keeps running through a process and it gets stuck in some kind of loop that we're not aware of, it kills the virtual machine before completely destroying the budget. So then with this, we also have like our software. How do we actually play microchess on the 6502? So for this case, we have our CPU here, and we have.
So can I jump in for a sec on that?
Yeah.
Just for the SSH thing. So we, one of the things is that at least right now, I think we're still charging for GPUs only when the machine is powered on. Unfortunately, what we found out is that, so this is a great, so the SSH will, if it's powered off, will go and power back on that VM before automatically for you, right? Which is, I think, a very useful tool for anything that's statically acquiring, that has this charging for things, especially GPUs, which are ridiculously expensive.
So let me just restate, just so that everybody caught what you were saying. So this isn't a built-in feature, but we just hacked around. So we figured out that some of the interfaces that were available meant that we could make it look like it was an on-demand SSH. So you SSH to this arbitrary name. It's not an IP address, but it's a name that will automatically get resolved using the OpenStack tools to an IP address. If that doesn't exist, if it's not ready, it will trigger OpenStack to bring our VM up. And then the other stuff that we're running inside the VM will, if we've got science experiments running, it will keep the machine running. If it detects, however, that we're all off of it and there's no experiments running, it will consider it idle and it will call the machine and shut it back down. So that way, Sanjay, I, CJ, Patrick, we're unaware of this. Our workflow doesn't change. But we also have a max timeout limit, you know, in case we fuck up, because I don't have infinite budget. The other thing that we really wanted, so those of you from the NERC clan, we really wanted access to our budget. So we would have actually stopped the machine if we were exceeding a budget. We couldn't figure out any interfaces for that.
Oh, yeah.
So that's just very practical, running data science-like experiments in the real world. We have to worry about money.
So we think like, oh, we're gonna be exploring these neural networks, gonna be diving into the depths of microchess, and we spent the first couple weeks like working with OpenStack and troubleshooting and.
Because the price of that GPU machine is expensive. On the other hand, as we got to the end of the semester, we really appreciated it. That GPU we have access to has what do I care? A fuckload of memory. And it really allows us to explore very complex neural network configurations. But it's expensive.
It's true. So back to microchess. So we have our 6502, our simulator, we have the microchess program, and so we're able to run it in a way where like you hit C to clear it. When you hit P, this is when the computer goes through its process and evaluates moves. So the computer is the group on top, it's the white pieces. And so when I hit P in my keyboard, it's going to go through a series of instructions where it figures out like, oh, these are all the possible moves I can make as my first move, and this is the move that I should do. And it chooses the most common move, opening move in chess as a result. As a human, you can also play against it. You select the piece, like for example, I select the pawn on square 63. It uses octal notation instead of traditional chess notation because it's easier for it to store. Move it to square 43, and so then you can move out that pawn, and then you can play against the computer again. The computer chooses like move the knight out here. You can also switch sides, which is helpful for us when like we don't have to know who's playing first, whether it's black or white. We can automatically put the computer on the top, and they're the ones that play. And then once you type Q, it provides a bunch of statistics about everything that happened as far as what the values of the registers are. But importantly, you can also see how many instructions were executed, how many were executed per second, and a bunch of other data. There's also a bunch of other flags that you can add to the 6502 that allow you to find the trace, dump it, add it to a file, and then work with it like you're able to do.
So in your use case, it's just send a board, you do the work, collect the trace, put the output. It's not like a full game. It's like one.
Yeah, we take each board state and then that's our game. Cool. Yeah, so then we go through collecting data. So we talked about the process of going from a PGN into a state vector itself. And so the PGN file is just a list of moves. It's not very helpful in telling you how the board looks unless you're able to visualize a chessboard in your head. So what we do is we convert those to FEN files, Forsyth-Edward notation, where we show on each of the 8 lines of the board, this is where the pieces are. This is how it's set up, whether the square is empty, whether it contains this pawn or anything like that. And then we are able to take that board state and then put it into the initial state vector for the microchess program and then run that. And once we run it through the 6502, that is our input state that we give it and the output state that it comes out with, as well as all of the traces in between.
So let me just point out something that these guys had to do, right? So got a chessboard, right? But that thing on the far right there, that UC board, that's a binary vector, right? So they went in, they reverse engineered where in the program the bytes are that represent the board. They figured out what that meant, and then they made a tool that just generates a bit vector that they can slam into a state of the program. And then automatically now the program's sitting at that board state. So that's already this idea that we're converting the world into just binary operations on states of register and memory.
And then you only store the vectors that are possibly like change in the system, right? Because there are some that will never change.
So the initial state that's put into the computer is the complete state. They get an entire end state and actually every state in between. But the study they do is that and they'll talk about this in a second, they're going to go and analyze of all the games they've ever played, which bits in the locations did ever change. And then for the sake of scalability for the moment, we only work with those.
And just to another point about one thing through this semester, we spent a lot of time working in a bottoms up kind of framework where we built a lot of low level tools. We built a tool that takes a PGN file and turns it into a FEN file. And we built a whole bunch of these tools to the point where now we can just run one script and it executes all of these scripts below it, which allows us in future semesters, we can build on top of this work. And like data collection can become a lot faster. Running actual experiments, as we'll see in a bit, can be a lot faster. And so like a lot of the going was slow, but we're hoping that this will accelerate like future developments as well.
Going off the question that was just asked, this is how we ended up taking the excitable bits, or in this case, we took the start state and an end state. And using an XOR, we were able to just find the specific bits in that start and end state play that were actually changed throughout the process. And then going through all of the games that we had, that's when we poured all these state vectors that we had of only the bits that were changed into one large OR state vector, which is our mask that we used to mask out on all the games the bits that we were actually sending through the neural network.
Just out of curiosity, did you ever check like in the test cases, like did you ever note in the test cases if these were the only bits, or like was there like a anomaly or something where some other bit also changed, like in the test cases?
So this was for both our training and our testing set
Okay.
for like our total data set, basically. We did look into it because we have a tool called, we call it SV info. What it does is it takes one of these state vectors and it tells you which bits are one and where they're located. So then we can use that and figure out like, wow, there's a whole bunch of bits between locations X and Y. That's probably the board that changed, or like, oh, all these in the end, this is determining whether black or white is the one to move. And then you can evaluate it from that way too, as far as like, oh, we created this process, but like just a heuristic check, is this actually working? We can go and look and see, like, does this make sense that this changed?
Just to clarify something for because just to make sure that you got it. So the mask
Yeah.
that says these locations change was evaluated for
Oh,
all
okay.
games, not just the training set, not just the test set.
Okay.
I'm sure they'll tell you the number, but it's about 690 bits, locations in the 64K vector that are actually changing from a start to an end when you consider all starts and ends.
This is totally lost, right? Like, there can't be a bit that ever changed that you don't accumulate in this mask.
Yeah, and then we can run it on, this is just specific to our data set right now. This is not specific to all board positions of all time put on microchess, but the goal is that in the future, when we start working with different data sets, larger data sets, that we'll be able to figure out and keep adding to this.
You just said that 64 kilobytes, you had only 600 some bits that were changed?
690 odd bits ever actually change from start to end.
So they may have changed as intermediate results, like it's.
Locations, right? These locations change
Yeah.
from start to end.
Mhm.
If a bit, you'd have to go through every state if you wanted to find out what bits ever changed. Because right
Well,
now,
these aren't
if
a lot
a
of
bit
bits.
got set back to its original.
Yeah.
We wouldn't be aware of it.
Yeah, so these are only the start and end states that we're
Right.
choosing, not all of the 14 million states in between where all the registers.
Sorry, I was wrong. So
Yeah, sorry. Yeah. it's a good-
But I'm gonna guess that they kind of like are containing to clear regions, right? They start to be, so those are the area probably of read-write memory that you have. Yeah.
So there's in fact, that's all the interesting stuff, right? How would we discover these? What do they mean?
They're the class.
But for the moment,
Sure.
we gotta start somewhere.
So then we also put these tools, because first when we started working, we did not use some more conventional neural network tools. We used something called FAN, Fast Artificial Neural Networks, which is run in C. And we used specifically float FAN. And so we had to build a few tools in order to convert these bits to floats. So that we only have 690 float values that are going used as inputs and outputs to our neural network. So that's what some of these tools are here. Validating our tools with tests, it's always important to test, and make sure that your tools are doing what they say they do, even when you're changing and in the middle of an experiment. To rerun these is always helpful. And then the process of actually running an experiment. So this is the first part is the collecting the data, and this goes to the second part where we have our data set. We want to take out like we have our layers of our neural network. We have what the input neurons will be. We have what the output neurons will be, which will be these bits that could possibly have changed. And we go through 4 phases where we set up whichever neural network configuration we're working with, whether it's either fan or PyTorch. We then go through and train on whatever percentage of the data we're choosing or whichever data set we want at that time. We then test on a unique data set that is separate from our training data set, and then go through a results process where we create a Jupyter notebook that calculates some basic metrics as well as includes other numbers that we can then work with further in that notebook. And each experiment that we run produces its own unique configuration of the neural network and its own notebook that you can go and run. So if we run this command once, it could produce, say, like 30 neural networks with all unique configurations, and then we can go in and figure out which ones work better, which ones didn't, and why. So these are some screenshots from the results notebook. We tracked local errors, which are in this file, in this specific board. It moved from start to end state, and it was supposed to predict that these 128 bits changed, but it actually predicted however many bits, and then we divide that by the total. And so you can see, like, just get a relative idea of which ones were more accurate. That's also why it's above 1, is because there are 690 bits total that change, but sometimes only like 110 bits change in this between the start and the end state, but our neural network predicted that 150 would change. And so dividing 150 by 110, you get another that's bigger than 1, things like that. We also graphed the total errors, which is like the global errors of all of our vectors, and the training loss function for every 10 epochs.
It's hard to read, without the 8 plots, I can see the title
Trial 2.
trial, oh, I see, so,
Yeah, so these are for each individual trial.
Which is a configuration of a neural network.
okay.
And also that ones on the left, those local errors that are above 1, that was all when we were using FAN, which is a very old tool, which is very brittle, and we're not even sure we used it right. But as soon as we switched over to using more modern
PyTorch.
tools, PyTorch and so on, we actually eliminate that. The neural networks actually get very good very fast.
Yeah. This is one of the results from one of the specific experiments that we did. So a specific neural network configuration. In this case, you can see in the top right, we started with the 690 changing bits starting in the end state. But in between, we had 3 hidden layers, double the size of the starting and the end state. So that gives the neural network a lot of flexibility to try to track what's going on in between the process of when it's predicting. But basically, we were able to see, out of 73 results for this experiment, we were able to see that 16 of them, only 8 bits were actually predicted incorrectly. So when it went from the start and the end state, its prediction was almost spot on, maybe off by 1 byte. But out of 1 byte in 690 bits that are changing and 6,000 total bytes in a state vector, that's not a lot of error that we're actually seeing.
For this one, I missed it. How do you divide the training and test data set?
So we randomly select in this specific experiment. We had 7 different games. Each game had a number of board states, and so we randomly assigned those board states to a training and a testing set.
What was the percentage
It was
split?
80-20 split. So
80 for training and 20 for testing.
yeah, that's a pretty typical.
Yeah.
But yeah, so that's how we did it.
I'm gonna miss this, but like just taking a step back, right? You're trying to replace 14 million instructions with a couple of matrix multiplies and then sigmoid or something, right? Like that's the idea, and you have 8 bits that are wrong. It seems like you're on something. That's like the big thing.
8 of them were predicted totally accurately. So you could have just run this neural network and you would have gotten the exact state that you would have run if you'd run 14 instructions.
And it's sort of ridiculous that it should have done this well with such little data. And it's actually also nonsense. We can get back.
Would it reduce your data set to use some kind of hyperparameter optimization?
Sure, actually, matter of fact, all kinds of things could be done at this point. A lot of this work was to set us up to start doing this kind of study, because there's actually the architecture of the network doing things that are much more interesting, like actually using, we all know as computer systems people, the fundamental unit is a byte. Restricting ourselves to only looking at the bits that change as the input, that seems ridiculous, right? There are all kinds of interesting things now for us to start exploring. Eric, I think you can.
Yeah, so I was gonna say, I asked, what is the what is the comparison between the computational cost of this neural net to the 14 million instructions you skipped? And what do you expect that to be once you have your hardware accelerators, et cetera?
Okay, so the second part of the question is potentially, yeah, and the first part, it's bullshit, right? I mean, this is a fucking huge GPU sucking up more power than that CPU for sure, despite it being my shitty C code that's running the 6502. The idea here is not so much this particular technology. Right now, we're just trying to study the baby steps.
Sure.
Is it even viable with no semantics to take a binary vector representation of a computer and infer that there is opportunity for acceleration?
Sure.
Now, the second part of what you said speaks directly to my original motivation. If you don't look at the crappy, pardon all the machine learning people here, the horrible things we as computer scientists have done to do machine learning, you actually look at, there's two parts of this community. There are those who have been studying it from a biological perspective, and those who have been simply making sure that Google can predict what we're about to type next, using a lot of computers and a lot of energy. Those who have studied the neurobiology suggest there are both scalable and power efficient implementations if we're willing to go radically different architecture.
Well, I've seen hugely efficient implementations once you have an architecture set, right? I watched the PhD thesis presentation at MIT about taking Hugging models and turning them into having the actual architecture in hardware. You fed the model to it, and it was now it kept up with real time and was as accurate as it was running on a GPU for hundredth of the cost.
Right, just most people aren't familiar, but you're right. That's so what Eric is saying is while everybody today, for those of us who are sort of not in the field, we hear about machine learning, it has to do with the matrix math that's being deployed on GPUs because that seems like the way we could get this to work. But there are other branches of machine learning that study if you knew the architecture. Like biology, you could grow or build a custom circuit that is radically more efficient. As a matter of fact, a lot of the most early interesting stuff on what is called neuromorphic computing demonstrated nano or picojoules to do an inference, not gigawatts of GPU energy.
Exactly.
Not that I have an opinion.
Yeah, there has been one particular thesis driving a lot. Yeah, so what this means as far as future deployment, or future development. So future directions for this project, we talked about a lot of them already, but applying them on different programs. On this program, we can apply them to more games. We can achieve larger scale. We can start to look at the full trace and pick different spots instead of just the start and the end states. And we can start to learn the actual representation of what is this computer doing? How is it able to calculate these ones? We can do them with more and less complex programs and see how our neural networks fare. We can also use like different architectures for our neural networks and continue to improve on that front. We can also start looking at new systems in the sense that they're more modern, such as a RISC-V architecture, x86. Goals and aspirations for the future is to find a model of execution somewhere, as well as achieving architecture independence, because our hypothesis is that we can find some model of a computer outside of the specific instruction set and everything to it that we can abstract away. And the goal is to continue building a concrete foundation for future data-driven.
Just want to highlight this last point because there have been plenty of my graduate students and folks who have put their heads against this. One of the big contributions these guys did is bring this into a world where we can now produce Jupyter notebooks, massive amounts of data. We are not the experts here. We don't claim to be the experts on machine learning. But now we can actually bring people into the fold to work on this problem, and they don't have to know that they're working on speeding up computers. They can do what they do well, and we can work with them in a really kind of seamless way. Now, of course, I don't know if Sanjay's on the call, so I can say whatever I want, and maybe you could say, no, that bullshit, I could never work with you guys, but. Oh, perfect. So then it is the best collaborative experience that he has ever had working with computer systems.
So I guess, have you tried the last closing the loop, so taking the inferred vector, putting it back into the machine state and
So so this piece of work right now, a lot of what we focused on was setting things up to
Sure.
do studies.
I
So
understand.
the past work has been all about, could we get any form of online real acceleration?
Mhm.
And then we exactly take an inference, we feed it back in, we take that inference, we feed it back in, and we can actually play forwards and backwards, but we're also very careful in that past work. This is ridiculous, right? We're saying the beginning of a move to the end of a move. In past work, where what we made the prediction problem was much more engineered and precise. We basically said, hey, look, you stand back, we're watching a reoccurring pattern.
Sure.
Let's make that thing the prediction problem is.
Mhm.
Because now that might be a front end of a loop, it might be the start of an interrupt.
Right.
Whatever the case be. When we were doing this, they were computationally bound work. We purposely chose loop heads.
Mhm.
And then we said 10,000 loop iterations forward, that's your
Mm.
task. Here, we just wanted to say, hey, look, we take something extreme,
Mhm.
an IO-driven interactive program with a complex algorithm behind it, and just say, semantically, the problem is, can you replace the entire algorithm? Which is roughly ridiculous, right? But we can ask the question concretely, we can study it, and now we can start exploring all kinds of interests. But the ask paper talks about how we recursed the networks and things like that.
no, but just here stupidly, I was just wondering. When you feed back your inference, does the program work? Or like one of those
Oh.
bits are actually physically. it's
Yeah,
more
I
fuzzy,
see what you're
right?
saying. So,
Can
yeah,
you-
so we only actually, to be honest, got real results towards the end of the semester because we finally got everything working. So, one of the two built that final tool that took our inference and put it back and ordered it into the original state. So, and now the nice thing is, yeah, we can drop it in place. Now, since we know that it's the ones that are bit perfect, of course it
should
plays.
work, yeah.
Now what we're doing is looking at ranking and clustering
Mhm.
where the errors are, what they are, because,
Mhm.
for instance, if it isn't right now, we're not doing anything, we're no filtering. If it's an intransient bit
Right.
that's right after, so right before read, then of course it won't make a difference. We're only starting that work now.
Yeah, okay. As well as if it's a MSB versus a LSB, right?
Yes,
That's gonna make a lot of difference.
This might already be clear, but in some of our other work, we worked something analogous to branch prediction, just at these larger intervals. So it had that property of, sure, you might pay for cost of incorrect predictions, but it's impossible to commit to incorrect computation. So that was like when we try to make this a little bit like tighter, those are the type of guarantees that you can provide.
Here is
Yeah.
less obvious that you can do that though, right?
Say again.
Here is less obvious that you can do that.
Yes, so what Tommy's talking about is when we actually took these ideas and built a system to actually achieve speed ups. This is the underlying study of the networks. So what Tommy's talking about is what we did to bypass this incorrect problem. What we do is we take the output of the neural network, right? We then pretend it's like a speculation. We take a core and speculate from there to get a new end state corresponding to that start state. We then put that into a cache. Now, if the computation hits and finds in the cache, then you jump to the end.
Sure.
And that we were able to demonstrate, as crude as it was. One, it can't make a mistake. Two, we were able to see that the system could achieve its theoretical speed up maximums, which in our case, it was a third speed up. Using nothing was parallel in the programming, but the implementation was completely parallel.
So I I'm taking this away from sort of the end results. Part of this talk, I think, is about, creating an environment where you can go and log into a computer, right? And just have lots of data and and computational resources available to you to work on in a very interactive fashion, right?
And
Now,
batch,
what's that?
and batch. You can also launch batch experiments if you want to sweep new parameters, generate new data and so on.
Yeah. Now, if I look at, so first of all, there's something that's turned out to be awfully broken in this, which isn't your fault at all, is that what we found out afterwards was that OpenStack reserves a GPU for you if you have a VM that's, even if it's powered off. So right now, I don't know if we're charging you for it or not yet, but the real charges someday will be, it doesn't matter if you power it off, which is insane to me, but that's not my, that is something we haven't been able to work around. Containers, on the other hand, do have this attribute where if it's off, then you don't, you end up freeing all the resources of it, except for the storage. I don't know that, but actually I'm curious if anybody from Red Hat's online is like, could we, this idea of being able to just log in interactively and have the machine powered down when it's not being used, that it seems like people by default, we had to do something special for our courses to have all these resources freed when you're not doing it. I don't know if OpenShift or OpenShift AI supports the releasing resources when it's not active. And this idea of just being able to use this as an interactive service in SSH and add an extra little bit of shim. Has anybody done that with the container environment? Is there any reason you wouldn't use containers for this?
Mainly because of all of our custom software. I mean, we're using specific tool chain, we're using our own C code. A lot of this was custom and we needed an environment that we were familiar with. If somebody was going to do the work and give us an environment of containers that do it all, great.
Like for the course, you create your own image with those.
So I didn't want to do that again.
Okay, so it's about the creating a custom container and stuff.
I mean, and I wanted these guys and Sanjay to basically just SSH.
Yeah, but it doesn't seem like a far stretch. But it seems like something we want to support. Like part of this is just a use case for what we need to provide to researchers that just want to have that interactive experience. Curious if anybody from Red Hat is online. And Thorsten, you have any opinions on this?
No, not really. Nothing that I could add and make it better from here.
This is something we should try to internalize and figure out how we can actually support exactly this kind of use case, because it seems like generically very interesting or very useful.
I had a question. So when you say architecture independence, do you mean that you have a accelerator that's attached that you're working with to do it, or the complete architecture independence?
So what we mean is that a binary vector representation of a computer is a binary representation of any computer, right? I mean, you can create ones and zeros. I don't really care what the instruction set was. I don't care what the code was. We're operating at the level of the underlying literal Turing configuration states of the machine. Now we've got other work where what we did was, so imagine the following. Let me start not with the state vectors. Let me start with something easier. Every machine, you can say, you could enumerate all of its opcodes, right? x86, it's a fucking huge number, like well over 4,000 plus unique opcodes, right? Now, if I took the opcodes of any computer, there's going to go from 0 to n, right? And then what I did was I said, okay, I'm just going to watch computation, and the most frequent, whatever the opcode is on both platforms, it's whatever its most frequent opcode is, I'm going to make that the 0 instruction opcode. And then I might see a different one. Then that becomes 1, and so on. Now what you can do is you can create a trace from both computers, right, with their opcode ranked index, per time unit, and you can plot it on the same graph, right? You can actually watch and plot two different computer executions, where X is time, Y is opcode range, right? And if I have a problem with scale, then I can scale. Now, think of this. If I now take a machine's state vector representation, which is very different, right? 6502 is 64K. We've done it with x86 machines. I think we've done two things. We've done sparse address spaces and we've done condensed address spaces to 4 gig. And now what you do is you do an XOR. So at every time step, instead of gathering the full state vector like these guys have done, you say, what is the XOR between this and the last state? Now you record the XOR, and you're gonna find that the XOR actually repeat, and now they become a dictionary, a token, or a new kind of instruction. Now you rank those by frequency, and you plot again. And we've done that, and it is fascinating. You can take microchess on x86, you can take microchess on 6502, you can plot them, and you will see that if you start expanding or contracting the timeline, all of a sudden you can find where they fit, which maybe is not that surprising. The x86 has about anywhere from a 1 to 9 instruction compression compared to 6502, because 6502 is a RISC-like architecture. If you use that dilation factor, all of a sudden the graphs start to look the same. So if you learned on the underlying structure what's going on, I'm going to argue that the neural net is actually learning something that is the actual property of the execution.
The algorithm rather than of the.
I'll say actually more than the algorithm. We demonstrated that it also includes the distribution on the input data. An algorithm is one thing, but a shortcut has to do with finding and exploiting things where the data and your algorithm are interacting.
Why didn't you, like, why did you, obviously the whole state vector here, 64,000 times 4K, 4 times 8. Why didn't you do the XOR? Because that would presumably be tremendously less data.
We do. I mean, our data set has all of it in there, but we just wanted a very straightforward, concrete problem that we could map to a prior thing we worked on. And ask was the easiest one for us to focus on.
Can I take one more swing at that question of architecture? I think it's really so like, you know, I think this chess thing is really cool, but you could take it or leave it, right? I think the real magic is in the transformation from a general purpose process, right? An instant in time, to an alternative representation that can be consumed by other hardware, right? So like, that is the first step of that independence, right? So going from like processor format to GPU format, right? But it's not just GPU format, it's a bit vector, right? That's an input that's amenable to just linear algebra, right? And like, holy crap, the processor there is math, right? So like, I think it's all about looking for these transformations, like the gather that takes it out of the CPU and into that new format, the scatter that brings it back into the processor format. You could start to wonder like, hey, can I start putting these transformations together? Can I take it off an x86 processor, put it on an ARM processor, right? Can I take it off that and put it back into math? So like the bigger idea of architecture independence is kind of in generalizing this transformation.
And there's evidence biologically that it's a multi-scale iterative process. We have parts of us that are operating in this moment in time, in this location, right? But our knowledge that makes us efficient with what we're doing right now is actually much slower and much more abstract, right? And somehow we take what's happening right now, we propagate it up, we get predictions on the way down that become localized to what we're doing now. So we wrote a proposal where we start talking about this idea as a piece of a much larger architecture where you imagine neural networks, or whatever you want to call them, state vector pairs and neural networks that are kind of being abstracted and abstracted and abstracted away, that then are going to be giving you predictions downward. Now, whether that goes to in the end to an x86, to an ARM, to a 6502, it's the, as you go downwards, you start specializing the prediction to your particular consumer. And the caches I talked about, in some sense, is the final realization of that. When I stick a state end and start end, that's to this fucking computer, this location, right? Now there's, again, this is obviously decades of ideas and research. So I'm happy to keep going, but I want these guys to be able to sit down. Again, I personally think it was an incredible haul to jump into this. And the very fact that they didn't go running in the middle of it with all the little pieces that we were trying to get working and validate was tremendous.
Sorry, is that a poor sign of intelligence? Really cool stuff. It's great.
Actually, already an hour anyway.